So good morning and good evening for everyone. And I am Mingu Yu from Princeton Plasma Physics Laboratory. And thanks for having me here and thanks for the introduction. So I'm very glad to share our experience of accelerating our code, which is GTS, using OpenACC. So our GTS code is a global gyrokinetic particle simulation code for microturbulence study in tokamak. The tokamak is a promising candidate for nuclear fusion reactor in the future. So for the numerical simulation, we adopted the particle in cell algorithm, which is the same as the Andrew's presentation. And our code is about over than 15 years or 10 years old, but we are still actively upgrading our code to attack the new type of the physical problem, such as the thermal panch transport in the tokamak. Before, we had no experience about the GPU machine because we had no GPU machine. But we attended the GPU hackathon in last year at Princeton University, and we learned basic functionalities of the OpenACC with great help of our mentor Ruben. As you all know, OpenACC was very easy to learn and very easy to apply to our code. So as a result, now we are running our code, running production simulations on the GPU machine, which is called Traverse at the Princeton University, with a significant acceleration, especially for the particle part. So we get over 20x for the particle parts. This a very significant speed up, but we have a similar problem that the field solver part is still a bit slower because our field solver part relies on the external libraries such as PASSI or HYPRE. They have some GPU version, but in our case we haven't got significant speed up by using GPU version. So we still stick on the CPU version of these HYPRE library. So what is the GTS code? The GTS code is to simulate the microturbulence in the tokamak. This is the tokamak geometry, and this is the poloidal plane, and this is the toroidal direction. And there are strong helical magnetic field inside the tokamak, so we have some curved linear coordinate and field aligned mesh, like the three-dimensional mesh like this. And we are using delta F particles inside code. And this code is mainly written in the Fortran and partly written in C. And this is previously parallelized using MPI plus OpenMP. But recently we are actually using pure MPI version for the CPU machine. And for the GPU machine, now we are using MPI plus OpenACC. So for the simulation of that very hard nuclear fusion plasma, we are using this Gyrokinetic Equation. So basically, we need to solve the temporal evolution of the electron and ion plasma temporally, but instead of dealing with the full 6-dimensional phase space, we reduced one velocity dimension. So we have 3D for space and 2D for velocity space, because in the tokamak there is a strong magnetic field and all the charged particles have this kind of gyro motion, and this gyro motion is so fast and it's not very interesting. So what we interested in is the motion of this guiding center. So we use the two velocity dimension, which is the parallel direction and perpendicular direction. So we can reduce the dimension of the problem to the 5-dimension, and we are solving this temporal evolution of the gyrocenter distribution function. So mathematically, this distribution function is continuous on 5-dimension, but we use the finite number of the Markov particles to approximately represent this continuous function. And on every particle we solve the equation of motion to simulate that trajectory of each charged particles, and also we evolve each particles weight, because we are using so-called delta simulation, which is the we only simulate some deviation from the prescribed S0 function. So this is the total particle distribution function, but we are interested in only the small deviation to simulate the small amplitude of the microturbulence. And to evolve this distribution function self-consistently, then we need to update our electric field with time. So we evolve the potential, plasma potential. So that we also solve this plasma equation, but this has some different form from the traditional plasma equation. But we are dealing with the guiding center, but we still need the real position of the particles. So we have this kind of gyrokinetic transform to get the real influence of the potential to each particle. So anyway, so we have this gyrokinetic classification, which on the right hand side, this is the charge density, and left hand side is the gyrokinetic Poisson operator. So by solving this equation, we can get the potential. Then using this potential, we update the particles, and with the updated particles, we update the potential. So this is the PIC algorithm, which is the particle in cell method. So there are many particles here in the cell, and we have some mesh, and the particle has their weight or position and everything about the particles. And on the mesh, the electric field or magnetic field are defined on this mesh grid node. So first of all, we assign some field information such as magnetic field or electric field on each particle. And we now have every information on each particle. So using that information, we solve the equation of motion and weight evolution equation. Then we move the particles' position and update their weight. So this is the moving routine. And after that, we deposit the particles' weight to the nearest neighboring 4 grid node, for example. So this is the depositing part. And after that, so we know the charge density at the mesh grid node, so we solve the plasma equation on that mesh. So we iterate this for temporal evolution of the plasma. So 3 out of these 4 main routines are about the particles. So these 3 routines depends on the number of the particles. The performance of these 3 routines depends on the number of the particles. So we accelerated our code routines about these particles using the OpenACC. And we still rely on the external libraries such as HYPRE for this Poisson solver or field solver. And these particle parts are very easily and efficiently parallelized by OpenACC or MPI because the particles are basically independent from the each particles. And it has a single level loop in terms of the parallelization. So very simple and very basic, simple ACC parallel directives is very efficient for huge number of particles, at least millions or billions particles. And most important thing from our experience for the performance is that the copy from the host to the device or from the device to host is a bottleneck of our simulation. So to remove that, we create all particle information as the global variables on the device side. So we don't need the communication from between the CPU and GPU, except some diagnostic routines. So, for example, the assigning fields to the particles, we just need this one ACC parallel loop directives with this present clauses. So we just find some nearest grid index and interpolating from the grid nodes to each particle and save some field information at each particle. This is the single parallelization, single level of the parallelization. And for the updating the particle information, move and update particle information the same as the previous. Accidentally, some particles can approach to the same node at the same time, then it can cause some problems. So to prevent that, we put this ACC atomic update for updating the node information. And fortunately, because our particles are quite random, so these some race condition or accessing the same point at the same time is very rare event. So we can still get very high speed up for this routine strand. So for the field solver, we have two types of the numerical modeling. So for the same equation. So for example, first one is the original way, is that we solve this coupled two equations on unstructured grid. So because the unstructured grid is quite a complicated shape, so we cannot deal with whole 3D-dimensional equation at the same time, but we separate the equation to the 2D equation and 1D equation, and we solve them iteratively. Another way is to use the structured grid, which is simpler. So we can use FDM method to discretize this equation, and we can solve the Poisson equation just by solve one. And these two types are different, but basically in terms of the numerical scheme, this is just a linearized AX equals B matrix equation. So just inverting matrix equation. So we rely on the some HYPRE library with and Boomer AMG method to solve this equation. And the HYPRE library has two versions, the CPU versions, and recently they are developing some GPU versions. But we still stick on the CPU version because of the performance. I describe this more at a later page. So, okay, so we now have the Trails cluster at the Princeton University, which has the 46 Power 9 nodes, and at each node it has 32 cores and 4 NVIDIA V100 GPUs. So we are using this extensively now. So now I'll show some performance comparison. So this is a very small case for the test. So just 9 million particles for this simulation. Just one node is used. And there are 4 different configurations. This blue is using 4 CPU only, and the black is the 32 CPU, and orange is the 4 CPU plus 4 GPU, and this yellow case is the 32 CPU plus 4 GPU. So you can see that the row is better, and this is the log scale. So you can see we get great speed up for almost everything, which we parallelize. We haven't parallelized all routines, but we parallelized the major routines, such as the push ion, moving the particles, or the charge ion or charge ion, which is the depositing the particles weight to the grid nodes, something like that. But for the Poisson routine, which is the field solver routine, we cannot parallelize using the GPU for this routine. So you can see that this blue and orange and this black and yellow has the same level of the time, because so GPU has no effect on that. For the speed up factor, we can get 100 speed up in the comparison with this yellow and blue. We have almost 100 speed up for the most of the particle routines. And for the whole speed up, we get almost 20 speed up between this blue and yellow. But blue is the only using 4 CPU and yellow use the 30 CPU. So this is not a fair comparison. So fair comparison is between this black and yellow. So yellow is the speed up only by the 4 GPU. So if you compare with this, then we can get almost 3 or 4 speed up depending on our number of the particles or situation. So still very nice. But our bottleneck is the field solver, because we haven't parallelized that field solver routine by using OpenACC. We rely on the external libraries. But for the most of the other routines, which is that depends on the number of the particles, they are very well accelerated. So this is the full capability of the one node. So when using 32 CPU, this breakdown, each routine, their computational costs are well balanced. And if we accelerate the particle routines, then these routines are squeezed, but this Poisson routine has not changed. So because of that, the Poisson routine is now our bottleneck. So for the more investigation about the speed subroutine, as I said, we have two types of different numerical modeling. So these two are original modeling on the unstructured mesh using FVM method, and this orange is the new numerical modeling on the structured grid. Because of that, original solver needs some iteration. So for the high accuracy, we need more iteration. So for high accuracy case is much slower than the low accuracy case because it needs maybe 2 times or 3 times more iterations inside. So it's very slow. So as you can see here, this Poisson routine has almost all of the time. The other routines, which is about the particles, they are all very small. But this single Poisson routine is very expensive now. So fortunately, the new solver has a smaller, has cheaper cost because it doesn't need the internal iteration inside because it deals with the 3-dimensional solver directly, so without decomposition to the 2D and 1D coupled equations. But still, this case is also the Poisson is still a bottleneck. So this is usually be shown in this pie graph. So for the original solvers, depending on our accuracy of the field solver, high accuracy shows very dominant elapsed time by the Poisson routines. But with the new Poisson routine, we have better balanced pie chart, but still this Poisson is the bottleneck for our code. So as I said, this Poisson routine depends on the external library. In this case, we are comparing the HYPRE and GAMG. HYPRE is by the HYPRE library, and GAMG is provided by the HESI library. And they both have the CPU versions and GPU versions. So for some simple test case, and I use the 4 MPI ranks with 4 GPUs. So the ratio between CPU and GPU is the 1. In this case, we can get some speed up by using GPU version of their libraries. But the speed up factor is just 2 or even smaller than 2 because of our, I guess, our small problem size. So our problem size is not very huge, so we can get the full advantage of the GPU. And even more problem is that actually we are using 32 CPU per 4 GPU. So in that case, in this case, this is the 4 GPU per 1 GPU. The reason why we are using still the many CPUs is that some of the routines are still need MPI acceleration. In that, for that routines, the more MPI ranks, better. So we still prefer to use the more MPI ranks, and in that case, the GPU version of the field solver libraries are even slower than CPU version because of their internal algorithm. These many CPU ranks per GPU is not preferred. I heard that. So for example, this blue is the pure CPU version of our code plus this HYPRE solver. In that case, this is very slow. But we accelerated the particle routines by using OpenACC. So this is represented by these GPUs. Then particle routines are now parallelized, but field solver parts are using different cases. Then, as you can see here, the best case is the GPU plus CPU version of the HYPRE. The elapsed time is very reduced, so we can get maybe 3 or 4 speed up. But if we use the GPU version of the field solvers, then in the Poisson routine, their performance becomes slower. So we are still working on this and looking for the better solution of to get full advantage of the GPU, even for this Poisson routine. But for now, we stick on this case. So GPU for the particles and CPU for the field solver. Okay, so this is a summary. So we are developing our code actively and using the OpenACC now. So this is very helpful to. So now our simulation cost is significantly reduced by using the OpenACC and the GPU. So this was great. And my impression was that it is very easy to learn and apply for basic functions, but for more advanced functionality, it's not, in my opinion, it's not easy to learn. But anyway, the OpenACC is very nice, and we have great speed up, and thanks to OpenACC people for this great speed up for us. Okay, so and I use my time, so I'll stop here. So thanks for the listening.